Today we're going to talk about something that is something you would have run into probably in 2126. I think I talked about it I taught somebody 2126 last year. I talked a bit about correlation and regression if my memory serves me correctly. That was the first time I taught that class in 11 years. But it's correlation. It's stuff that you've run into before. That said, that shouldn't mean that you don't ask questions. Just because it's material that you've run into before doesn't mean that I expect that you know it perfectly. Everything we've talked about so far has looked at differences between means. I mean, other than exploratory data analysis, everything we've talked about has been about differences between means of different groups and their scores, right? You can also look at, if you just sort of kind of tilt your head sideways kind of thing, you can think about the differences between two groups as a relationship between an independent and an dependent variable. Right? Let's draw a quick picture on the board here. Because, I mean, we normally think of, if we have two groups, let's just make the simplest possible design, and we have two groups, and we're going to look at percent correct in a memory task. Okay, how about that, a memory task, and you're going to have 0 drinks and 5 drinks, obviously with alcohol. We would probably look at data like this and say, yeah, great. And that's a group difference. But we can also think of this as a relationship between two variables. These two variables are the independent variable, right, and the dependent variable. So we can think of it the same way. It's just a different way of looking at it. So we're saying that, in this case, as drinks increase, memory decreases, right? You see that? So you see what I'm saying here? Does it make sense? Okay, let's put the screen back down. So you can certainly think of it that way, and it's a completely reasonable thing to think of stuff that way. And with a continuous variable, so here we talked about a variable that had two possible levels, and 0 drinks and 5 drinks. If we talked about a continuous variable, like the relationship between, well, it's a very simple one that we think about a lot, height and weight. As height goes up, weight goes up. Now, I don't know which is independent and which is dependent in that case. It doesn't really matter. But as one variable increases, the other one increases. Okay. So with a continuous variable, that's a variable that can take an infinite number of possible values. As one goes up, the other one goes up. And you can take it from a scatter plot or a log. Right? Make sense so far? Good? Okay. So scatter plots are great. Here's one that I wish was this tight. This is income and IQ. There actually is a pretty strong correlation between income and IQ. It's about 0.5. That said, if that's not a 0.5 correlation, that's really a tight correlation. But let's pretend that that's true. So that's, you can have an infinite number of possible incomes and an infinite number, basically, of possible IQs. It's not really infinite, but let's put that over here. And the scatter plot is, of course, a very useful EDA tool. We would maybe use it there more than anywhere. But we would also use it in this case if we were interested in the relationship between, well, IQ and income. So what we need is a standardized way to look at variable relationships, even if they have different scales. Because IQ is a scale and income is a scale. Right? They're both scales. But they're measuring different things, and we want to have a way that we can standardize this kind of stuff. So we can look at the relationship between IQ and income, and it doesn't matter what currency you use, or it doesn't matter what IQ test you use. I mean, it would matter a little bit, the IQ test, because they all measure somewhat subtly different things. IQ tests are pretty good though. Don't let anybody tell you different. They predict all kinds of things. Exactly what they should predict. Okay. So one way we can let's start here is something called covariance, which the name should tell you what it means. It means the amount of variance two things share. And here's the formula for covariance, which is the covariance of x and y, that's just two different variables, x and y, is the sum of x minus x bar times y minus y bar divided by big N minus y. Number of pairs of observations is what big N is here, minus 1. That's the covariance of x and y. So you can see if you take a look at first of all, this looks like a variance except we have x and y, not just x and x. Right, because normally we would have x minus x bar squared, which is just x minus x bar times x minus x bar. What we have here is x minus x bar times y minus y bar. We're looking at two separate variables. So this measures the degree to which two variables vary together, or covariate, hence the name. If deviations from x bar and y bar go in the same direction, you're going to get a positive covariance. The difference between covariance and regular variance is covariance can be negative. Variance can't be because it's a squared quantity. This isn't a squared quantity, it's just two things multiplied together. And if, as you can probably see here, just look at the formula, if deviations from x and y go in the same direction, in other words, they're both positive or both negative, this is going to be a positive number on top. If, as one goes up, the other one goes down, a negative covariance is what you get. Okay? So the sign actually tells you the direction of the relationship, and the value tells you how much the two things overlap. How much the variances overlap. You have to start thinking for the next week and a half, think of variance as a thing. I mean, hopefully you've kind of been doing that intuitively throughout the course because of analysis of variance. But here, we're not talking about ANOVA, we're talking about covariance, but it's still a variance. So you've got to think about variance as a thing. Do the variances overlap? Okay? Now, the next thing we want is we want to standardize this relationship because it's going to depend upon a lot of things, and one of those things that will depend upon is the scale. We want to standardize covariance so scales don't matter. So if the income and IQ, if your income is measured in dollars or it's measured in cents, it shouldn't make a difference. If it's measured in Canadian dollars or American dollars, it shouldn't make a difference. Measured in rubles, you're in real trouble. Rubles, the currency of the Russian Federation, which is now basically worthless. For those of you who have not been paying attention to the news, so it shouldn't matter if incomes are reported in euros or dollars or pounds or whatever. So we want to standardize this thing. And the covariance depends upon variance, or standard deviation variance, of x and y. So if it depends on those things, let's divide by those things. If it depends on those things, let's divide by those things, and that'll allow us to have a standard measure of association. We have a standard measure of association. Any questions so far? So what we end up with is this, which is the covariance of xy divided by s sub x times s sub y. And that's called the Pearson correlation, or Pearson R. If the covariance, the absolute value of the covariance of xy, equals s sub x times s sub y, then the absolute value of r equals 1. You have actually a perfect relationship. This is just basically, it's a proportion of variance, shared variance divided by all the variance. Right? Shared variance is covariance xy. S sub x times S sub y is all the variance. So we're thinking of variance like a thing. And it's how much do they overlap. So if you have, so again, let me just pull this up, draw a picture. And here, this is fine. There's two different, sure. So if covariance, so here's the variance in x. Here's the variance in y. Right? And you can see there's an overlap. This is the covariance of x and y that you get. So if you do a Venn diagram, you got x and y. The part where x and y overlap is the covariance. Okay? Now, if in fact, let's pretend that the thing we're measuring is going to be height in centimeters. That's the variance of height in centimeters of everyone in the room. And let's say we now did the height of everybody in the room in inches, going back to the cycloplots. They overlap completely, don't they? They have to. But we know they're different scales, the numbers are going to come out different, but, because again, get back to the assignment 1, but the thing they're measuring is exactly the same thing. They're both measuring height. In that case, we have perfect overlap. And then we get a covariance of 1. Okay? Does that help at all? That's good? Make a Venn diagram. The sign of R, the plus or the minus, just talks about direction. All it does. And I know that you've run into this many times before. You're in third year psychology. You have read papers that have correlation coefficients. So the sign of R simply shows the direction. And I'm pretty sure I did talk about this last year in 2016. Good chunky. How many of you actually took 21, 26 with me last year? Okay. So you were lucky. Everyone else had PO before masters. It's a funny joke between our friends. Apparently Paul said something really mean about me the other day. What did he say? I want to know because I'm going to that son of a bitch. What? Well, joke. That's the jokes. It's the blind joke. Was it a blind joke?
Yeah.
Excellent. If I don't make fun of somebody, less chance I'm friends with them. I got a course evaluation once that said, it's very unprofessional that he makes fun of his colleagues. It's like, no, they're actually my friends. I do that to their face, too. We're like that. We're friends. Yes, I want a lecture from how to be professional from someone who never comes to class. Anyway, I'm just assuming that. I threw that in. I don't know if that's true, but there's something like that. Let's just pretend. So R can only be between -1 and +1. It can't be bigger. Because think about that. It's a proportion of how much overlap there is. Can there be more overlap than all of the overlap? Well, no. So if you do a correlation by hand, which no one does these things by hand. What do you mean, your mind? But if you were to do it by hand, and you got a value greater than 1 or less than -1, you've made a mistake. It's mathematically impossible for it to be less than -1 or greater than +1. It can't happen. It's not a thing. It's straight lines only, so remember, it can't be curves. This simply deals with straight relationships, straight line relationships. No curves. unless you want to be pedantic and say a straight line is a curve, and that's fine. I quite like pedantic. So a straight line only. So if you have like a dose-response curve, like we talk about neuropharmacology all the time, we have a low dose, and then a medium dose, and then a high dose, and you get this like very little effect, big effect, and then very little, well, let's say on behavior. If you give rats morphine, and you give them a low dose, it doesn't do a whole lot. You give them like a medium-sized dose, and they tend to run around a lot more. It's called a taming effect. They're a little less frightened of being out in the world because they're full of heroin. And then you give them a high dose, they just sit in the corner going, because they're strung out on morphine, right? So we get that kind of relationship a lot in life science in general. We get, like sort of people often talk about inverted U function or parabola. And a lot of those dose response curves are actually perfect parabolas. The problem is this would show that as a zero correlation. Okay, so you got to keep that in mind. It's got to be straight lines. There are ways to measure curvilinear relationships. What's the word I'm looking for? They're the same idea. They're doing the same thing. They're just doing it a little bit differently. One of the base assumptions of this is that it's a straight line. Okay. Now, we should be able then to predict y from x. We should be able to predict y from x. Because if we've got a scatter plot, we end up with, take a look at that. We should be able to predict your height from your weight. Or your weight from your height. Right? You should be able to take one and look at it and put a number into it, like an equation, and just predict it. So, in essence, you could draw a line through a scatter plot, right? And figure out what the equation was of that line, and you'd have a prediction. Now, there's an infinite number of possible solutions to this question of what line do you draw? So let's put this back up again, and we'll put a scatter plot up. So if I put a scatter plot, let's put some dots. I don't know what we're measuring. There, let's say it is height and weight. So we've got height here and weight here, and that would be in centimeters, and that would be in kilograms. Okay, so we would know that as one goes up, the other one goes up. The question is, we want to find a solution to this problem, and the problem is how will we predict y, centimeters, from kilos? Okay, well, I could do this, and just eyeball it. That looks pretty good. Maybe it should be more like this. Maybe like that, maybe like this one. They're all going in the same direction because the lines seem to go in that direction, but how do we pick which one? I mean, there's obviously bad ones. Here's another solution. That one's wrong, because that says as height goes up, weight goes down, and that's not true. We could also come up with a perfect solution that would always predict all these values, and it would work like this. You just connect all the freaking dots. Would that be useful at all? Well, no. First of all, I don't know how you get the equation of that line, is question one. But question two is, all you're saying is, oh, if I measure both things, I can predict them. Oh, yes, of course you can. That's like saying, okay, I'm going to do a card trick. Pick a card. But here, let me demonstrate. Let's pretend. Take a card. You got a card in your head? What's your card?
Ace of Hearts.
It's the Ace of Hearts. See? Pretty good. I'm magic. It'd be better if I could just know the Ace of Hearts by a line, but no. I have both values now. I have your prediction and my prediction. Done. Would have been good if I would have just pulled it It's an old student, maybe you've seen him in town, Ryan McFarlane, he used to go to school here. He's a psych degree, he's a magician. He was pretty good, and he took this class, I remember him taking this class, and I remember him sitting in class, just like playing with cards. I was like, excuse stop it, because I want to watch your act. I was his academic advisor. I remember he'd be sitting in my office, we'd be taking courses, and he'd be like pulling scarves out of his hand, like just doing magic all the time. It's fun. All I can do is this. So that's a solution, but it's a shitty solution. It's not, because you need to know both things. We want to just know one thing and predict the other. It's one of these lines, as one goes up, the other one goes up. The question is how to do it, and the way is using what's called the least squares regression line. Okay? It's not the only solution. Like I said, there are literally an infinite number of solutions. It's just one that we all agree is a really good solution. Okay? So basically what's happened is over the years, statisticians have, and you know, scientists in general have come up with this sort of consensus that this is the best solution, is the least squares regression. So here's the idea. I don't even know what these things are measuring, but what I've got here is I've got some data points. Okay? These are y's. And then I have a line, and we'll call the line y hat. And it bothers me that it's y hat and not y circumflex, because it's not a freaking hat, it's a circumflex. But, and I keep meaning, and I say this every year, to ask a francophone colleague if they call it y chapeau, avec un chapeau, or y circumflex. I kind of hope they say avec un chapeau just for the hell of it. Anyway, y hat, because it's got a little hat, and y. Okay, these are also y's down here, I just don't have it labeled like yet. So what we want to do is minimize the sum of these deviations of y from y hat. In fact, we want to make it so those are going to sum to 0. So it's going to overpredict as much as it underpredicts. We want it to overpredict as much, because these are prediction mistakes. These differences, that are called residuals, y minus y hat, they are mistakes. The line is wrong. The stupid line where you connect all the dots is actually right. It's not a very elegant solution. And it has, think about it, it has no degrees of freedom. In other words, I have to know everything to know the solution. I don't want to have to know everything. I want to have some data points and come up with a solution, and I don't have to know every single point in the universe. So we want to minimize the sum of y minus y hat, and we're going to square it, because if we do y minus y hat, it'll come to 0. So we're just going to square it. Oh, it's going to be sums of squares. Big surprise there. So what you end up with is a prediction equation. You get something like this. It says y hat equals a plus bx. And yes, I know that many of you would have learned in high school or elementary school that y equals mx plus b. And yes, I know the b now means something entirely. In fact, it means the opposite thing in the formula. And it's not my fault. Blame someone else. I think it was probably Putin's fault. Yes. So we get this pretty simple equation. That's just a linear function. It's just a line. Right? So y hat equals a plus bx. That's the predicted y equals the intercept, which is just where x equals 0, plus the slope of the line times the x value. Okay? So y hat equals a plus bx. Now, another way you'll see this written is instead y hat equals b sub 0 plus b sub 1 x, or x1. And that's a more general way to talk about this. So when you talk, usually, if you're only talking about simple linear regression, which is what this is, you often will see y hat equals a plus bx. But if you're talking about regression in general, you would say y hat equals b sub 0 plus b sub 1 x sub 1. They're the same thing, they're equivalent. So we're going to get a predicted value that's going to equal the intercept plus the slope times x. So when you think about it, now, anybody here have kids? Anybody here around a lot of little kids maybe? When you take like a baby into the doctor for checkups, which you do a lot in the first year, what they'll do is that they measure how long. They don't say tall until they can stand up a little bit. So how long your kid is, and then they'll weigh your kid, and they'll say what the doc is doing, and he or she probably didn't even know this. They just put it into an equation, and they look it up, and they say, okay, that's right, that's fine. Development's fine. The kid's the right weight for their length, right? They just want to see if the kid's growing properly, right? And sometimes they'll say that it's in a certain percentile, right? So whatever. The point here is that they're using a regression equation. To calculate my salary, there is a formula that's just like this. There's a floor, that's the intercept, plus the number of years I've worked here, times, which is the x, times the amount of increment you get every year, which is kind of like the slope. Okay, so you actually deal with things like this all the time. You just don't think of them as regression equations. And I mean, when it's for figuring out someone's salary who works at the university, it's not, because we all follow exactly on the line. There are no residuals. There can't be. It's in our contract that that's what we calculate our salaries. Okay. So we're going to get predict y with the intercept plus the slope times the x value, whatever that x value is. Questions about that? Oh, there it is. Good. I lost my pointer for a second there. So if you want to find B and A, this is one of those things that you never do by hand. It's so easy to make mistakes. Like if you've got, first of all, you got to calculate covariance of x and y and divide it by the variance of x. So if you're doing this by hand, first of all, you're doing a variance by hand, which is a pain. But then you're also doing the covariance by hand, which is, again, another place to make mechanical errors. No one does these things by hand. You might do it once in an intro stats class just to see how it works, but as a rule, people don't do these things by hand. On the other hand, there are statistical techniques that you do by hand. I was helping one of my honor students with her data analysis this morning, and I just did it by hand because it was literally quicker than firing up a computer program, because it took me 45 seconds to do, and that's not some magic thing. I had to do 4 calculations with a calculator. But this would take you perhaps hours to get a correlation coefficient. You don't do that. And then for A, it's the average score for y minus the slope times the average score for x. So this is how you find out what B and A are. Okay. Any questions up to now? Good. Okay. it's very tempting to see a value in an equation and think that it's all very meaningful because, oh, it's math. It's extremely tempting. So the value of A, which is the intercept, which is where x equals 0, it's not always meaningful. There's times, in fact, when it doesn't make any sense at all. It's in a lot of respects, it's a mathematical artifact. So if you had, let's see, what's something that adults do that kids don't do? I've got to think of an example. How about income? Kids don't make money, as a rule. And if we were to predict someone's income based on their age, we could. It's not, it's not the only variable, but as a rule, as you get older, you make more money each year. You also, believe me, have more expenses, but as you get older, you make more money. We could predict then how much money someone makes based on their age. It wouldn't be perfect, but we can get it. We can get a regression equation. Sure. Okay. We get something, and we would have a value where x equals 0. In other words, where age equals 0, and you'd get a number. Would that number be meaningful? Not really. Do babies have incomes as soon as they're born? Probably some do, right? But most of us know. So it's more, in that case, it's just a mathematical artifact. It's like that's where the line hits the y-axis, where x equals 0. Right? Now, in some cases, and let's use the example of the figuring out someone's salary, what you actually can do, seriously, if you want to figure out any of our salaries, look at the collective agreement, it's a public document. Or you can wait till the end of March and find out when they publish all of our salaries and make over $100,000 a year because we're supposed to be somehow embarrassed that we make money. Never understood the value of that. Old colleague of mine used to say it's the list of people want to steal from. Oh, Broadbank makes that much money, but he's got a nice TV, let's take his stuff. So in that case, the floor is that salary floor, where x equals 0. That is actually meaningful, because you could be hired right in the graduate school with no experience, and you get 0 steps in that case. It's like that. But something like the amount of money you make as a human, depending on your age, is not a very the intercept wouldn't be very meaningful. So in that case, it's just not meaningful. And you can only do linear relationships. So again, just to keep that in mind, it's only straight lines. This shows the importance of exploratory data analysis. So when you are going to do anything with correlations, the first thing you want to do is look at the scatter plot and see if there actually is a relationship. And you might say, oh, I see a relationship, but if it's a curvilinear relationship, right? So if it's a curve, you'll say, I can't use these techniques. There are other techniques. All you do is instead of what you're doing is you're fitting a line. So if you're fitting a straight line, all the math here assumes you're fitting a straight line. If you're fitting a curve, it's the same idea, but it's how much they differ from a given curve. So then you have to know what the curve is, that's all. So conceptually, that's what I was looking for before, it's exactly the same thing, just the math is different. How do you know there's linear relationships or not? The easiest thing to do is look at the residuals. Well, the easiest thing, I guess, is a scatter plot, but one of the things you can do is look at the residuals. So you can do what's called a residual plot. And as noted, there will be 2 questions about residual plots on the final exam. A residual plot is a pretty simple graph. It has this axis, the x-axis has the x value, and then on the y-axis you have the residuals. And we have 0 here, and then you look. And if it's all equally distributed, if it overpredicts as much as it underpredicts, you've got a straight line. Okay? So if it overpredicts as much as it underpredicts, you get a straight line. You can get residual plots in SPSS or any other stats package simply by just clicking a box that says, show me the residual plots as well, please. Okay, so you just ask for the residual plots. If you got something that looked, so that was fine. So in fact, let's say that was on the final exam and it looked like that, you'd say, let's say the question was, are there any problems with residual plots here? And if you saw that, you would say, no, there's no problem at all. That's fine. It's a linear relationship. Maybe I am magic. Oh, there it is. Okay. That's funny. I couldn't see it from right beside it, but from the other angle. Oh, yeah, there it is. So let's change the dots. Let's change it around a bit. This one we're overpredicting, underpredicting, overpredicting, underpredicting. What would that residual plot tell you? What would that residual plot tell you? About the relationship between these two variables. Yeah, just say something.
No, it's not linear.
It's not linear, and in what way?
It is not over-predicting and under-predicting the same amount.
That's true. The prediction error depends on the x value. What kind of relationship do we probably have in this case? What's it look like? Looks like we have a curve, right? We have something that probably looks like this. It looks like that. To the curve. What if we had something look like this? That's also no good, because it's actually, it starts to predict, the prediction is very small, and then as the x value gets bigger, they get bigger as well. So that's telling you it's not a straight line. You can draw there are straight line solutions, they just aren't the best possible solution. So in this case, the prediction error is very small, and then it gets bigger as x gets bigger. That's the problem. So the easiest thing to do is to look both at scatter plots and look at residual plots, because both of those things will tell you about what kind of relationship you actually have. So in other words, the covariance of x and e, of the x variable and the residual, should be 0, or something very close to 0. They should share no variance. And in fact, again, in any stats package, you could ask for it to output the residuals into a variable. And then all you do is just run find out the covariance between x and e. It should be 0. Or very close to 0. It's probably not going to be exactly 0. If it's exactly 0, you might have made up your data. Also, don't go outside the range. So I talked, this is sort of like the thing about the 0, the intercept isn't always meaningful. If you go outside the range, it's not very meaningful either. So again, let's use the example of how to calculate faculty member salary here. There's a base of, so we'll call that the intercept, right? That's the base, that's the floor. And then there's the number of years, that's the x. And then there's how much you get an increase every year, a couple $1,000. So let's just pretend that the base salary for me, for a full professor, is 120,000. I can't remember what it is. And then it's 2,000 times the number of years. Okay. So you can say Dave's been doing this for this. He's been there's where. Yeah, but if you'd worked 1,000 years, if you've been working at the university for 1,000 years, and you multiply that times 2,000, or 1,000 times 10, you could make millions. you can't work with the university for 1,000 years, even though it feels like it. So you can't go outside the range of what the data are, and it's so tempting. You have this prediction equation. So it's so tempting when you look and go, oh, it just says here that y hat equals a plus bx. Well, I'll just sub those numbers in. You can't really do that. You shouldn't. The prediction equation is for data that have the range that you have collected data for. It may be the case that actually it can predict outside the range, but it doesn't necessarily have to. So you have to be really careful with that. Right? I don't know if I told you this, but there's an old friend of mine was trying to figure out how to predict how many cigarettes people smoke per day, based instead of on a physiological measurement. That's very easy to do with just getting a saliva sample, because you can measure cotinine, which is a stable metabolite of nicotine, and it has a half-life of like 24 hours. So it's a very nice stable metabolite. So you can just measure that cotinine in saliva, and you can say how many cigarettes somebody smokes a day. The problem is you have to send their saliva off to a lab. It would be nice if you could just ask them a few questions, and you can get it too. So he tried to come up with a behavioral measurement. So we had people at the Ontario Science Centre in Toronto, which is a great place to get research volunteers, because it's people who are interested in science. So you set up a little table. Would you fill this out? So we had this thing, if you're a smoker, come fill out this survey. And people gave a saliva sample, and he measured all these things, and he also measured, so he's measuring cigarettes per day, but that they reported. And then he's measuring all kinds of other things, whatever they were. And one of the variables he asked about was how old they were when they started smoking. And it turned out that it did a pretty good job, along with some other variables, in predicting how many cigarettes people smoke per day. So you get a regression equation. You can't look at that and go, oh, okay, so how many cigarettes on average do the 3-year-olds smoke? You can't really do that. Right? The youngest person on the list was like 10 or 9. Like, that was when they started. It wasn't a 10-year-old smoker. It was 1987. These days look like more people smoke than there were a lot of 10-year-olds in Canada smoking. So in that case, you can't really go outside that range. You can't say, oh, well, let's see, what's a 7-year-old? How many do they smoke? So if you're 7-year-old smokers, well, they're a whole different population. You can't go outside the range. It's really important. Like I said, though, it's so tempting. You look and you see math, and we've been taught through our whole lives that if someone writes down this equals this, well, that's just true. And you got to remember all the assumptions in the background, which is this means that this equals this if it's a linear thing, if you don't go outside the range, you blah, blah, blah. You've got to keep that in mind. Okay. Questions about this stuff? Pretty sure you've run into it before? Pretty sure. Got nothing? All right.